Welcome back to the Explainer, first semester BCA students. Today, we're tackling a massive part of your syllabus, Unit 2, covering logic and counting. But, I really want you to think of this as way more than just another syllabus requirement to memorize for your exams. What we're looking at here are the very foundations of computer science. Seriously, every complex algorithm you're going to write, every piece of software you compile, and basically every app you use on a daily basis is fundamentally built on the exact bedrock we're about to cover right now. So let's get into it. Okay, let's dive into this. Here is our roadmap for the Explainer today. First up, the fundamentals of logic. Then, advanced logical concepts. Next, the basics of counting. And finally, permutations and combinations.
Starting off with Section 1, Fundamentals of Logic, or as I like to think of it, the true and false binary switches.
To really understand how computers think, we first have to wrap our heads around propositional logic. Basically, this is a branch of logic dealing entirely with propositions, which are just statements that are strictly 100% either true or false. Think about the processor sitting inside your laptop right now. It doesn't understand conversational English, it doesn't get nuance, it literally just understands electricity. It reads digital switches that can only be on, which we call true, or off, which we call false. To put that into perspective, your computer's processor evaluates billions of these true and false propositions every single second. In this specific realm of logic, there is absolutely no maybe. It's an absolute toggling binary. Now, we can link these simple true and false switches together using what we call logical connectives. There are three main actors you really need to remember here: and, or, and not. The and connective means your output is true only if both inputs are true. Think of it like two physical switches wired in a series. Electricity is only going to flow to the light bulb if both are closed. Then we have the or connective, which means the output is true if at least one input is true. It's like two switches running in parallel. If either one of them is closed, boom, the circuit works. And finally, the not connective. This one simply reverses the truth value. It acts like an inverter switch, basically flipping true to false and false to true.
So how do we keep track of all these complex combinations? We construct what's known as a truth table. Let's mentally animate this process, row by row. Step 1, identify all your variables. Usually you'll see these labeled as P and Q. Step 2, list out all the possible true and false combinations for those specific variables. And step 3, evaluate your logical connective row by row based purely on those inputs. By building this table systematically, you map out exactly how your logical switches are going to behave under every single possible condition. Breaking it down step by step like this keeps your cognitive load totally manageable and makes sure you don't miss a single edge case. Let's move on and see how this builds in Section 2, Advanced Logical Concepts. This is where we start balancing the scales of logic.
A massive concept in their syllabus is logic equivalence. This happens when two completely different logical statements somehow yield the exact same truth values in their final column on a truth table. Visually, I want you to picture this exactly like finding two completely different mathematical equations that balance perfectly on a scale. Even if the left side looks totally different from the right side, their fundamental value is identical. In computer science, this is a real game changer because it allows programmers to take complex, messy code and simplify it into equivalent statements that run way, way faster. But what happens when the scales don't balance? Enter tautologies and contradictions. A tautology is a statement that evaluates as always true, no matter what inputs you feed into it. On the flip side, a contradiction is a statement that is always false, again, no matter the inputs. And this brilliantly illustrates how logic can tip entirely to one side or the other. If you write code that's a tautology, well, it's basically just a redundant rule. If it's a contradiction, that's a total dead end that your program is literally never going to get past. Recognizing these extremes is absolutely key when you're out there debugging your future programs.
Okay, so we've got the rules down. We know exactly how the switches work. But here is the big question. How do we actually count the possibilities? Logic gives us the strict structure, sure, but we need combinatorics to actually quantify the massive sets of data governed by all these rules. That brings us right into Section 3, the basics of counting, where we shift gears and start quantifying our data.
A core concept here in discrete structures is the famously named pigeonhole principle. It states that if n items are put into m containers and your n is strictly greater than your m, then at least one container must contain more than one item. The classic visual metaphor is, well, exactly what it sounds like. Imagine you have a flock of 10 pigeons, right? But you only have 9 wooden pigeonhole boxes for them to nest in. No matter how you distribute them, it is a mathematical guarantee that at least one box is going to end up with 2 pigeons stuffed inside.
Let's step through the logic of applying this, because it's super straightforward. Step 1, count your items. That's your N. Step 2, count your available containers, your M. Step 3, compare them. If your items outnumber your containers, a container simply must be shared. It feels so incredibly intuitive when broken down like this, doesn't it? It almost sounds a bit too simple to be a university-level math concept. But trust me, its applications in computing are absolutely profound.
So, the crucial point is, how does this highly abstract idea apply to real-world computer science? Well, a perfect example is hashing. Hashing algorithms assign pieces of data, which we call keys, to a limited number of slots in a hash table. Now, because the universe of possible data keys is almost always larger than the number of available slots, meaning, yep, we have more pigeons than pigeonholes, the pigeonhole principle mathematically guarantees that a collision will eventually happen. 2 distinct pieces of data are going to try to jam themselves into the exact same slot. Knowing this mathematical certainty is vital for designing efficient load balancing algorithms and duplicate detection systems, so your software handles those unavoidable collisions smoothly.
All right, home stretch. Section 4, permutations and combinations. Let's arrange that data. In computer science, we constantly need to know how many distinct ways data can be grouped. To do this, we use 2 primary methods: permutations and combinations. Honestly, the main difference between the two boils down to one simple question. Does order matter? In a permutation, order definitely matters. Think of a spinning combination lock, which actually, scratch that, it really should be called a permutation lock. The sequence 1, 2, 3 is entirely different from 3, 2, 1, right? Only one is going to open it. Now, a combination is when order doesn't matter at all. Think of being dealt a hand of distinct playing cards. Whether you pick up the King of Hearts first or the Ace of Spades first, it doesn't matter. You still hold the exact same mathematical grouping in your hand.
Now, what's really interesting about this slide is how perfectly these concepts map to the exact problems you're going to face in your syllabus this semester. For permutations where order matters, you might be asked to find the number of distinct mathematical arrangements of the letters in the word mission. Because there are duplicate S's and I's in there, the order of every unique letter totally changes the final arrangement. For combinations where order is irrelevant, you're going to see problems like calculating the number of ways to choose 4 distinct cards from a standard pack of 52 playing cards. Getting this distinction locked in early is the absolute key to mastering combinatorics.
Wow, we have covered a tremendous amount of ground today. You've mastered the true and false rules of propositional logic and the structural laws of counting and combinatorics. But here is the provocative question I want to leave you with as we wrap things up. How will we physically structure all of this data to be used by complex algorithms when we hit Unit 3? As you start preparing for your next set of lectures on matrices, trees, and graph theory, I want you to remember this. Every single complex data structure you build is going to rely directly on the logical gates and counting principles you just learned today. Thanks so much for joining me for this explainer, and keep questioning how all the data fits together.